So far in the course, we've discussed statistics that assume that the data is normally distributed. In many cases, data is not normally distributed, or we aren't sure about the distribution of the data. This is especially the case when we're working with large data sets where it would be a lot of work to check to make sure that every single variable is normally distributed, or every single correlation has normally distributed residuals, etc. In these cases, it may be useful to use non-parametric statistics. The way that many non-parametric statistics work is by rank ordering the data. In this way, the data are converted to ordinal data instead of interval or ratio data. And in most cases, even when we are looking at scores of things, in many cases you would consider them to be more ordinal than interval, but anyway, that's beside the point. If one score on the BDI is a 5, that's a very low depression score, and the next highest score is a 30, a very high depression score, then those scores are now adjacent to one another. One would be ranked a 1, and the other would be ranked a 2. Okay, if you had 3 scores, 3 BDI scores, one was a 5, one was a 30, and one was a 31, those would now be 1, 2, and 3. If we're ranking the data, if we're converting it to ordinal data. Think about a foot race. The space between the runners isn't consistent. The space between first place and second place may be close, but the space between second and third might be very large. Again, we're ranking the data, we're converting the data to ordinal data. In fact, many data sets are non-normal. Distributions of BDI scores, BDI is the Beck Depression Inventory, in case you don't know. Distributions of BDI-2 scores often look like the chart here when randomly sampled. Okay, there are many people with low scores. There's a lot of people over here that have low scores, and only a few people over here on this end of the distribution with very high BDI-2 scores. This is a distribution that's heavily positively skewed. It's not normal. In these cases, we may want to consider using ranked data. As Andy Field says in the book, parametric tests only have more statistical power when assumptions are met. We're talking about power. We're talking about the type 2 error rate. Okay, so a statistical test that has a lot of power has a low type 2 error rate. In cases where assumptions aren't met, it isn't clear what the power of a parametric test would be. Parametric tests only have more power when the assumptions are met. In other cases, it's who knows what the power would be. It's going to be variable. As you'll see, what all of these tests tend to do is convert the difference between sums of observed ranks and sums of expected ranks, and then convert that to a standardized score, a z-score, for example, to evaluate the significance, just as we normally would with a standardized score. In the Wilcoxon rank sum test, ranks for each group are summed. Then the sum of ranks from either the smallest group, or if the groups are equal, the smallest rank, is compared to what would be expected if the ranks were random. This test is kind of the non-parametric equivalent of an independent samples t-test. Okay? I've presented 2 versions of the same formula here. I won't ask you about the computation for the exam this time, but know that the rank sums for each group are compared to what would be expected if the ranks were similar across the 2 groups. In other words, if the ranks were random across the 2 groups. If we have 2 groups of ranks and there's no difference between the 2 groups, then there should be some high ranks and some low ranks in both groups. But if we find that one group has more high ranks or more low ranks than would be expected, then we infer that these groups are different. There are more people with higher scores in this group than this group. Okay? We expect that the ranks are going to be random across the two groups. The Wilcoxon signed rank test is used to test the difference between dependent means. So this is analogous to the dependent samples t-test, the paired samples t-test. You would use this test for repeated measures design for samples that are dependent. Again, the difference is converted to, the difference between the ranks at two occasions is converted to a standardized score, a z-score, and you compare the z-score to a z-score distribution to evaluate statistical significance, just as you would with any z-score. The Kruskal-Wallis test is analogous to a factorial ANOVA. You can test multiple independent means. Scores are ranked for each independent variable. Then the sums of those ranks are compared to the expected random ranks. In this case, instead of comparing the results to a z-distribution, results are compared to another distribution called a chi-square distribution, and the chi-square distribution is used to test significance. But again, the idea is the same. We're comparing the observed sums of ranks to what we would expect the sum of random ranks to look like. So if there's a big difference between the sums of ranks that we observe and what we would expect if ranks were random, then we would say that those two groups look different, especially if they fall outside the 95th percentile for the chi-square distribution. Friedman's ANOVA is analogous to a repeated measures ANOVA, or, well, it's kind of analogous to repeated measures ANOVA. Repeated measures ANOVA would also allow you to have between subjects factors and within subjects factors. Friedman's ANOVA is really just for within subjects factors. It compares the ranks across testing occasions within a person. So again, we're looking at ranks, but this time we're looking at within subject ranks. So on the first testing occasion, we look at one person. Okay, we look at an individual. On the first testing occasion, let's say there's 3 testing occasions. On the first testing occasion, is that the lowest score? Is that rank of 1? And then is the second a rank of 2? And is the third a rank of 3? If it were random, we might expect the first occasion to be a 2, the second to be a 1, the third to be a 3, or something along those lines. Okay, and then we compare we look at this pattern of within subject ranks for each person. Okay, and then we compare that to a chi-square distribution using the formula there. Again, I won't be asking you about the formula. You can find more about Friedman's ANOVA in the field text. Resampling statistics are another non-parametric statistical technique and are near and dear to my heart. They're not in the, well, bootstrapping is in the field text. Shuffling and permutation tests aren't in the field test, though. But with parametric statistics, you assume a distribution and you compare your statistics to the assumed distribution. With rank-based statistics, the distribution is uniform. It's totally random. Every rank has an equal chance of being either in a control or experimental condition if you're comparing means, or they have an equal chance of being in one variable or another variable if you're computing a correlation or regression. By comparison with resampling statistics, you estimate the distribution that the data came from. So, in one way, parametric statistics assume a distribution. Rank-based statistics assume no distribution. It's entirely random. With resampling statistics, you estimate the distribution that the data came from. When we bootstrap, we take out individual scores. We take out a small sample of our data. We compute statistics on that sample. And we repeat it 1,000 or so times, or 10,000 times, or 5,000 times. 1,000's a pretty good number. 1,000 works pretty well. But in this way, we mitigate the effect of any single outliers. And we have multiple estimates for the population that we can use to have a better guess at the actual distribution of the data. So in a way, we're treating the data that we've collected as the population, and we're sampling from that population. And we're doing that a gazillion times, and then that kind of gives us an idea what the distribution might look like. And here's an example of what bootstrapping kind of looks like with data. So in the purple line is what the t-distribution looks like. And in the blue, this is a histogram showing how many of each value. So we have a lot of values that were 0 and only a few that were 5. But this shows you what the bootstrapping looks like. So on for trial 1 we got 1.5, and for trial 2 we got a 2, and then over 1,000 trials it starts to look something like this. Okay, and you see it's pretty close to a t-distribution, but not quite. It's a little different. And so again, we can estimate the actual distribution that the data came from, and bootstrapping does a pretty good job of that. Shuffling or permutation testing of the data is a little different. It's similar to bootstrapping, but it's a little different. So with bootstrapping, we take out a small portion of the data, we compute statistics on it, we put it back in, we take another sample out. When we shuffle or permute the data, we're shuffling all the participants and their data. So for one shuffle, participant 1 is paired with participant 4's data. In another shuffle, participant 4 is paired with participant 10's data, etc. For all the participants, we do it all at once. You can see here, so this is what the original data looks like, and now we're shuffling. Okay, so we're putting some of the cases into the controls, some of the controls into the cases, and we do that over and over and over and over again. In this case, we expect there to be no relationship between the variables, the correlations, means, or whatever statistic you choose. They should be about random. That's okay. Then we can shuffle about 1,000 times, and we can create a distribution of means or correlations or some other test statistic or whatever, and we can compare the shuffled data to our observed data. And our observed correlations, means, or whatever statistics that we're using, if they're below the 2.5 percentile or above the 97.5 percentile, we would consider them significant. They would at an alpha level of 0.05, at a p-value of 0.05. And the percentiles you choose will depend on whatever type 1 error rate you're willing to accept. So, in other words, with resampling statistics, we resample over and over and over again from our sample. The resampling helps us to accurately characterize the distribution which the scores came from. Another way to think about it is this. We're conducting the same experiment 1,000 times. In this way, these statistics are very robust to weird data. Extremely robust. And to me, they give me a lot of confidence in the results of my statistics. These statistics that I get, they're not just a fluke. Okay? So I really like resampling statistics. I think they're really interesting. I think they were really difficult to do in the past. You really need fast computers to shuffle data 1,000 times, or to bootstrap 1,000 times or 10,000 times. And with the way computer, as cheap and as fast as computers are nowadays, it's easier, and so more and more people are doing these kinds of statistics, and they really like them, and they're really great. Again, I think they give people a lot of confidence in the results, in their results. That is it for the course. Thank you, everybody, for your attention. Sorry that this is coming Monday night instead of yesterday. I didn't get around to it in time, but hopefully I'll have enough time to take a look. I kept it nice and short. There will only be a couple questions on non-parametric statistics on the test. The test is mostly going to cover the other things that we went over in the course already. Have a great rest of the summer, and farewell. And hopefully I wish you all good luck with any statistical endeavors you take in the future. Thanks so much. Bye.